In this video tutorial, we're going to be looking at a worked example for a reversible air source heat pump. Now, reversible air source heat pumps can be used in both heating and cooling applications. So they can be used to heat a room or a space, or they can be used to air condition a space. In this first example, we're going to be looking at the air source heat pump in forward bias, and in this instance, it's going to be used to heat a room. In the next video, we'll see how a similar device can be used for cooling or air conditioning. So on the screen here, we have a schematic diagram for our air source heat pump consisting of compressor, condenser, expansion valve and evaporator. And we also have PV and TS diagrams to represent that cycle. Now, directly underneath the diagrams, we have a descriptive question. And what we're going to be doing is we're going to be extracting information from the written question, as well as from our PV and TS diagrams. And I'll explain this as we go through the process. So to begin with then, on our schematic diagram, we can see that we have a compressor. So our refrigerant is being compressed before it enters the condenser. When the refrigerant enters the condenser, it's very hot, so it's going to give up heat energy to the room as it changes state. We then expand the refrigerant, and the reason for expanding the refrigerant after we've removed that heat is to allow its temperature to drop even more significantly. The evaporator then, in the case of an air source heat pump, is located outside. So we'll just make a note here that our evaporator is outside. So we have the very cold refrigerant entering a heat exchanger that's located outside, and therefore the air is going to heat the refrigerant within that heat exchanger. The warmer refrigerant then re-enters the compressor, where it's compressed, which is once again going to increase the temperature of the refrigerant even further before it re-enters the heat exchanger in the room. So in our descriptive question here, we're told that a reversible air source heat pump operates on the ideal vapor compression cycle and uses refrigerant R134A. It then goes on to tell us that details of the refrigerant can be found in the Thermodynamic properties document for Freon R134A. If you don't already have access to that document, then you can Google Thermodynamic properties for Freon R134A and you can download the PDF of that document. Next then, it tells us that when the air source heat pump is providing heat, the condenser operates at 1100 kilopascals and the evaporator operates at 250 kilopascals. So if we refer to our PV diagram and our schematic diagram, we can see that if our condenser operates at 1100 kilopascals, then P2 and P3 must be 1100 kilopascals. That's confirmed by our PV diagram because we can see our upper pressure here is the same for both position 2 and position 3. So let's make a note then. P2 equals P3, which equals 1100 kilopascals when our air source heat pump is being used for heating applications. It also tells us that our evaporator operates at 250 kilopascals, and we can see that the entrance to our evaporator is position 4 and the exit is position 1. Again, referring to our pressure volume diagram, we can see we have constant pressure for positions 4 and positions 1. So once again, we can make a note, P1 equals P4 equals 250 kPa. Next, it tells us that the compressor consumes 5.94 kilowatts of power. I'm going to make a note further down the page for this. P in, which is the power in by the compressor, equals 5.94 kilowatts. So what is the question actually asking us to do? First of all, it asks us to determine the enthalpy of the refrigerant at each position in the cycle. So we need to find H1 through to H4. In addition, determine the mass flow rate of the refrigerant, so m dot, the rate at which heat is supplied to the room. Well, the rate at which heat is supplied to the room is the rate at which heat is lost by our refrigerant. So phi out of the refrigerant is also something we need to determine. And finally, we need to determine our coefficient of performance. Okay, so let's clear some space And then we're going to use our thermodynamic properties document for Freon R134A in order to determine the enthalpy at each of our 4 locations. So let's begin by finding out enthalpy at position 1. Well, what do we know about position 1? We know position 1 is the entrance to our compressor. We know the pressure is 250 kilopascals, and if we refer to our temperature, enthalpy and pressure volume diagrams, we can also see we have dry saturated vapour here and here entering the compressor. Therefore, H1 equals Hg at 250 kPa. Now, whilst we're referring to our thermodynamic properties tables there, we're also going to determine S1, the entropy. And S1 will also be Sg at 250 kilopascals. Now, the reason we're going to determine S1 as well as H1 is because if we refer to our temperature entropy diagram, we can see that the entropy at position 2 equals the entropy at position 1. We have a constant entropy process. Therefore, S1 equals S2. And we're going to determine the value of S1 and S2 using the thermodynamic properties table. So let's refer to that document now. We're looking for Hg and Sg at 250 kilopascals. So here we have the thermodynamic properties document for Freon R134A. And the first few pages give us additional information about the refrigerant. And when we get to page 5 here, we can see that we have the property tables for our saturated vapour. Now recall that we have a pressure of 250 kilopascals. So we're referring to our pressure column here. And we're looking for a value of 250 kilopascals. So as we scroll down, our first page goes up to 51.14. Our second page then, we're looking for a pressure of 250 kilopascals. Well, as we pan down that column, we can see that we have a value of 243.39, which corresponds with a temperature of -5 degrees, and we have a value of 252.74, which corresponds with a temperature of -4 degrees. What that tells us already is that the temperature of the vapour there is somewhere between -4 and -5. Now, we haven't been asked to determine that, but as that's our reference column on the left-hand side, we're going to make a note of those two temperatures. What we're actually trying to determine is Hg and Sg when the pressure's 250 kilopascals. Now, once again, we're going to need to use a linear interpolation process here. But if we track along and make a note of our corresponding values, at a temperature of -4 degrees, our Hg value is 396.4. And at -5 degrees, we have 395.9. And the entropy values corresponding there are 1.7302 and 1.7308. So I'm going to transfer all of that information across: the temperatures, the pressures, the enthalpies and the entropies, and then we're going to determine our enthalpy and our entropy of our vapour at 250 kilopascals. Okay, so I've transferred our values from the thermodynamic properties document. We have the pressure, enthalpy and entropy corresponding with -5 degrees, and we have the pressure, enthalpy and entropy corresponding with -4 degrees. Now recall that we're trying to find the enthalpy and entropy when we have a pressure of 250 kilopascals. So we're going to use a linear interpolation process. Now hopefully you recall that to do a linear interpolation process, we need to find, as a decimal, the distance from our lower limit to our desired value when compared to the distance between our lower limit and the upper value. We represent that distance as a decimal, and then we can determine the equivalent enthalpy using that decimal and the equivalent entropy using that decimal. So first of all then, to determine the decimal, we need to use our pressures. And we're going to carry out the following calculation. First of all, to evaluate the shorter line, we have 250 minus 243.39. And to evaluate the longer line, we have our upper limit, 252.74, minus our lower limit, 243.39. Now that gives us a decimal equal to 0.70695. Okay, so the difference between our upper and lower enthalpies, represented by this distance here, is 396.4 minus 395.9. Well, that actually equals 0.5. So the difference between our upper and lower enthalpies there is 0.5. But we're interested in where we sit on that continuum, so we need to multiply by our decimal, 0.70695, which gives us 0.353. And that's the distance represented by our shorter arrow here, 0.353. So in order to find the enthalpy that corresponds with our 250 kilopascals, we need to add our lower enthalpy of 395.9 to this shorter distance here, which equals 396.3 accurate to one decimal place. So let's make a note of that enthalpy. Enthalpy 1 on the left-hand side, 396.3. And that's kilojoules per kilogram. Now we can repeat for our entropy, because we can see the distance between our upper and lower entropy values there is 0.0006. Multiplying by our fraction, 0.70695, gives us 0.00042. Now we need to take a little care here, because the shorter line that we have drawn there represents our 0.00042, but notice that our higher entropy value is on the left-hand side and our lower entropy value is on the right-hand side. Therefore, in this case, we need to do the 1.7308 and we need to subtract the 0.00042. That's going to give us a value between our upper and lower entropy values there. Well, when we do that, we get an entropy of 1.7304 to 4 decimal places. So once again, let's make a note on our left-hand side, 1.7304 kilojoules per kilogram Kelvin. Now note that that's our entropy value for both S1 and S2. So now we know the entropy at position 2, and we know the pressure at position 2, up in the top left-hand corner. We can now determine the enthalpy at position 2 from our thermodynamic properties tables. But what else do we know about position 2? Well, if we refer to our temperature entropy diagram, we know that position 2 is superheated vapour. So we're going to go to our superheated vapour tables at 1100 kilopascals, and we're going to look up our entropy of 1.7304 in order to determine the corresponding enthalpy value. So we know that the superheated tables come much later in the document, so we need to scroll down to the superheated tables, and we're looking for a pressure of 1100 kilopascals. Note that the two tables here are for 120 kilopascals and 130, so we need to keep going. And when we get to page 39, we have our pressures of 1100 kilopascals or 1100 kilopascals. Now recall that we had an entropy value of 1.7304. Well, here we have an entropy value of 1.7186, and here we have an entropy value of 1.7362. So our 1.7304 sits between those two values. Therefore, we know the temperature of our refrigerant is between 45 and 50 degrees. Again, the question doesn't ask us to determine that, but it's useful for reference. And we have corresponding enthalpy values of 423.4 and 429. So once again, we're going to transfer that information across. And we're going to use our linear interpolation method to determine H2, which corresponds with an entropy of 1.7304. Okay, so now we have our values corresponding with 45 degrees for entropy and enthalpy, and we have our values corresponding with 50 degrees for both entropy and enthalpy. Now, as we know, at position 2, our entropy is 1.7304. So once again, it sits somewhere between the upper and lower limits there. We need to determine this distance as a fraction. And the distance as a fraction is going to be 1.7304 minus 1.7186, all divided by 1.7362, which is our upper limit, minus our lower limit, 1.7186, giving us a fraction equal to 0.67045. The full distance here between our two enthalpy values is 429 minus 423.4, which is 5.6. Therefore, our shorter distance here is 5.6 times our fraction. 5.6 times 0.67045 gives us 3.75 to 2 decimal places. So this distance here is 3.75. Adding 3.75 onto 423.4 gives us our enthalpy value corresponding with an entropy of 1.7304 equal to 427.2. So again, making a note on our left hand side, H2 equals 427.2 kilojoules per kilogram. So next then, we need to determine H3. So what do we know about position 3? Well, we know that the pressure at position 3 is 1100 kilopascals. It's our higher pressure. We also know that we have wet saturated vapour because it sits on the wet saturated vapour line here and here. So for H3, we're looking at the HF value at 1100 kilopascals. So if we return to our tables, and we need to return to our saturated vapour tables near the top, and this time we're looking for a pressure, the second column from the left, of 1100 kilopascals. So before we had 250 kilopascals, we see highlighted there. Our higher pressure of 1100 kilopascals sits further down the document, so we have our pressure. And we know that our desired pressure sits between 1073.26 and 1101.93. We see the temperatures for reference, and we're interested in the enthalpy of the wet saturated vapour. Recall that that's represented by HF. And we have an enthalpy corresponding with 42 degrees of 259.6 and corresponding with 43 degrees of 261.1. Now once again we're going to transfer the information back across, taking care to ensure that our temperatures, pressures and enthalpies correspond with the correct values. So 42 degrees corresponds with the lower pressure and the lower enthalpy, and the higher temperature of 43 degrees corresponds with the higher pressure and the higher enthalpy. Okay, so we have a pressure of 1100 kilopascals, and we need to determine this distance as a fraction. So we do 1100 minus 1073.26 divided by 1101.93 minus 1073.26, giving us a decimal equal to 0.93268. The difference between our lower enthalpy value and our upper enthalpy value here is 261.1 minus 259.6, which is 1.5, multiplied by our 0.9268, gives us an enthalpy of 1.39, and adding our 1.39 onto our 259.6 gives us an enthalpy corresponding with 1100 kilopascals equal to 261.0. So let's make a note. H3, 261.0 kilojoules per kilogram. Now, the other thing that we know is that our throttling process is a constant enthalpy process. When we expand our refrigerant through the expansion valve, the enthalpy at positions 3 and 4 remains constant. And that's always the case for the ideal vapor compression cycle. So therefore, we know that H3 also equals H4. Therefore, H4 also equals 261.0 kilojoules per kilogram. So now we're on the home stretch because we need to determine the mass flow rate of our refrigerant, the rate of heat energy leaving the vapour, and the coefficient of performance. So we know from earlier tutorials that Pin equals the mass flow rate times the enthalpy of the vapour leaving the compressor minus the enthalpy of the vapour entering the compressor. Well, in this instance, we know H2, we know H1, and we know Pin, but we don't know m dot. So we can divide each side by the difference in enthalpy, H2 minus H1. And we get m dot equals Pin over H2 minus H1. Well, we know Pin is 5.94 kilowatts. And I'm going to leave it in kilowatts because our enthalpy values are in kilojoules per kilogram. Both the numerator and the denominator there are times 10 to the power of 3. H2, 427.2, minus H1, 396.3, gives us a mass flow rate equal to 0.19223, accurate to 5 decimal places. And we know our units for that are kilograms per second. Phi out then, which is the rate of heat energy leaving the refrigerant or entering the room. Well, we can see that that process takes place in the condenser, so between positions 3 and 2. So phi out is m dot H3, the enthalpy leaving the condenser, minus H2, the enthalpy entering the condenser. We have 0.19223 times H3, 261.0, minus H2, 427.2, which gives us a phi out value equal to minus 31.95. And our units there are kilowatts. The reason it's minus is because energy is leaving the refrigerant. So in actual fact, the heat energy gained by the room is 31.95 kilowatts. So our coefficient of performance then? Well, when we calculate our coefficient of performance, we need to use the magnitude of heat energy being lost by the refrigerant because that's the same as the heat energy being gained by the room. So we have the magnitude of phi out over Pin, or in this case, 31.95 over 5.94, giving us a coefficient of performance equal to 5.4, and that's accurate to 1 decimal place. So just a quick summary then. We used our thermodynamic properties tables and the information we knew about the vapour or the refrigerant in order to determine our enthalpy values at positions 1, 2, 3 and 4. Once we had our enthalpy values at positions 1, 2, 3 and 4, we was able to determine our mass flow rate of our refrigerant because we knew how much power the compressor was using or how much power the compressor was inputting into the refrigerant. Once we had the mass flow rate, we was able to determine the rate of heat energy being transferred to the room. And finally, we was able to determine the coefficient of performance, which is the ratio of the amount of heat being gained by the room when divided by the amount of work being inputted by the compressor. The amount of work being inputted by the compressor would also equal the rate at which electricity was being consumed by the compressor. So that ratio gives us an indication of how efficiently this particular device is working. In the next video, we're going to look at a similar example, except our reversible air source heat pump is going to be run in reverse in order to provide a cooling effect or an air conditioning effect to our room.